Okay, so welcome to this last seminar of the year, but it will not be the last seminar of the season, as we will have one more in January, more specifically the 19th of January, with Amadeus Misuda talking about beta CFI stars. So I just also wanted to remind you that our call for application is open for the next season of the Good Vibration Seminar. I get that you must have, that all of you must have received it by different channels. If not, please mention it to me. I will make sure that it reaches you. So right now we are welcoming Gábor Kovács for the Good Vibration Seminar, the last one of the year. We asked Robert Zabo, his PhD supervisor, to introduce him briefly. Thank you, Robert. The floor is yours.
Thank you very much. Hi, everyone. It's my pleasure to introduce Gábor, who works in my research group, which is the MTA Lendület Near Field Cosmology Research Group. And also this group is part of a larger one that we call SPECS, which is Space Photometry, Stellar Pulsations and Exoplanets. And Gábor focuses on stellar pulsations. So this is the largest group with a lot of observers and data analysts, but Gábor is pursuing theoretical studies. He started his BSc and MSc at the ELTE University, Eötvös Loránd University in Budapest, and he did his MSc already on modeling pulsations. And later on, and during still his university studies, he was admitted to the Konkoly Observatory Research Assistant Program. We started this program 5 years ago to attract the best students from the universities, and students can work on 3 different topics. Most of them are observers or working on data analysis problems. The second one was started later, which focuses on numerical modeling, large simulations, using supercomputers, GPUs, and the like. And Gábor was one of the first ones of these numerical research assistants. And the third one is engineering, which is also quite popular. Gábor is I would say, a guru of programming. He uses GPU, CPU, supercomputers, and he's very good at that, much better than I ever did or I ever was. He also teaches astroinformatics and programming at the Eötvös University. He's halfway through his PhD studies, so he's not on the job market as yet, but we thought that this is an excellent opportunity for him to summarize all the work he did so far. And as most of you know, the PhD takes a little bit more time for people who work on theoretical fields, especially if someone runs very long simulations, as Gábor does. He's very clever, bright, and I'm delighted to see that he's advancing on many topics. He is going to talk about these in a minute. And I would also like to add that he continues the line that was started by Robert Bushler, Géza Kovács here at Konkoly Observatory, Zoltán Kollát, and myself. So I think that's enough about his CV, and I wish him good luck with his talk.
Thank you for the introduction. So thank you for the opportunity. As Robert said, I working on multidimensional stellar pulsation modeling, and I'd just like to show one of these. For example, so this. Here we can see a fundamental mode RL iris, simulation calculated with the spheres pulsation code. This is a large array simulation model, and in this video we can see how the convection and the pulsation connect to each other. The colors shows the temperature, and the arrows show the convective velocities. Here we can see that the uprising motions are somewhat slower, and downward convective velocities are always done in a thinner tube. And so in this seminar, I will talk about these hydrodynamical models. And although many people think this may be a closed topic, but there are several unanswered questions related to these objects even today. This can be interesting from an astroseismological perspective too, since there are found newly found non-radial pulsation in Aralides stars, and this is interesting if we compare the several modes of the sun. We have the classical variables here, where the L is 0, and we have a small n modes. And the theory says that we expect the non-radial modes here in this little question mark, but observations showing that we have pulsation modes farther out at the L between 7 and 9 area. The usual way of modeling these stars are leading through the nonlinear hydrodynamical models, which, at least in the one-dimensional case, are not adequate for non-radial pulsations. So my topic is around these numerical modes, numerical codes. Besides, I also want to emphasize again that this is this study is in a work in progress mode, and my results are currently in preliminary stage. When I'm talking about classical pulsators, I mean the variable stars from the classical instability strip, like delta cepheids and Aralides and type 2 cepheids. And in this talk, I will concentrate on only Aralides and even a narrower part of them, the fundamental mode Aralides or RAVs. One of the most fascinating results of the modern photometric surveys are these observations of non-radial motion of Aralides stars. Here in this Patterson diagram, we have already stars.
Sorry, Gábor, you have this this thing occulting your title in your slide. Could you remove? Yeah. Okay. Perfect. Thank you. Ah, no, it's here again. Yes. No, it's okay. Thank you.
This.
Yes, that's good. Oh, yeah. This this is the control. Yeah.
Yeah.
Buttons of Zoom.
I'm trying not to move the mouse. Okay, so in this Patterson diagram, we can see that at the 0.61 times the main pulsation period, we have several stars, and there is another group here, and these pulsations are not connected to the radial pulsation modes. They are non-radial pulsations, and models showing that these modes come from, as I earlier mentioned, L between 7 and 9 modes. But the interesting thing is that these modes shouldn't be observable because they should be damped. And this is why we need the non-radial modes, because the current theory doesn't give back us these results. And there are other effects too. For example, in the Kepler space mission, there were found period doubling for Blaschko RLIs, and they showed that these Blaschko RLIs have period doubling in one of the Blaschko periods, and in the another there is no period doubling, which leads us to the conclusion that the Blaschko modeling is not stable modulation of the star. And the Blaschko effect. This type of phases and amplitude modulation is unsolved for for more than 100 years. And it seems that the key to answer this question lies in the multidimensional hydrodynamical codes. And this is the catch, that in the light of the new discoveries, our current one-dimensional models are not adequate anymore, and we need to move to the models which treats generally multidimensional phenomena like convection in 3 or 2D. But one may ask the question, why we even need convection? Because we modeling the stellar envelope, and in these stars the envelope is mostly radiative, and we have 4 convections, but we are away from that, and of course there is convection in the atmosphere, but we are not interested in that too. So why we have convection? To show this, let's see a textbook example. The criterion for convection is the Schwarzschild criterion, which says that the temperature gradient in the star exceeds the adiabatic temperature gradient, then convection will occur. So let's take a simple Eddington model and a simple adiabatic model. And if we calculate these gradients, we get that the convection depends on opacity. And opacity is important because the pulsation of these stars are driven by the Kappa mechanism, which is founded on the opacity change and in the opacity peak of the partially ionized hydrogen and helium zones. Here in this plot, we can see that the Kappa has a high peak in these regions, and this means that there is convection there. So in our models, we need convection. The question is how we will treat that, and this has an interesting history. So a lifetime ago, in the 60s, some scientists, besides working on the nuclear bomb hydrodynamics, started to work on a less destructive topic, for example, stellar pulsations. The first numerical models in this topic are credited to Robert Christie, who used only radiative models like these. The main goal was at this time to reproduce the instability strip, and for the blue edge of the strip, it was adequate, but it cannot describe the red edge. It was later shown by Baker et al. That we need convection for the red edge, but the standard mixing length theory was bad because it made the red edge too red. Here in this figure, we can see that the empty circles are stable models and the field circles are the positional unstable models. And we can see that this is way too low temperature. So the need for a time-dependent convection theory arise. And the main pioneers for this treatment are Gaff on Unno and Castor. And Castor's never published manuscript was the basis of Stellingwer's work, whose diffusion approximation were used for model surveys. And this type of convection handling in one dimension solved the mystery for the red edge. And meanwhile, the discovery of double mode pulsations lead the attention to the model selection problem. And meanwhile, this type of convection handling were started to use in the stellar core and for the core mixing. For the development was done by Hufus and Xiong, while Gimmel and Winkler performed the revision and the derivation for the models. And it was in 1992, which is 3 years before my birth. So it was really a while ago. The one-dimensional theories were put into practice by multiple numerical codes. And for the Christie's work was continued by Castor and Stellingwer. And the Stellingwer's code gave the foundation for every other code since then. For example, Dolphy and Feutinger and Marco and Bono as well as Marconi used the original Stellingwer code for the calculations, while Buchler, Moscali, Collat, and their co-workers converted the originally Lagrangian approach to an adaptive grid. And this is how the Budapest Florida code came into existence. This code was the first which successfully gave back double mode RLIs and Cepheids, and extensive surveys were made with it. The physical model behind this code, however, is a modified version of Gimmel and Winkler, and it lacks the backward convection, which created a controversy among the developers. Moskalik and Smolek argued that this treatment of convection creates an artificial damping, and this caused the presence of double modes, and then this is rather numerical and not a physical effect in this way. To prove that right, Smolek developed the Warsaw code, which can be distinguished from the Budapest Florida only in the allowance of the negative convective flux, whereas it cannot show the double mode pulsations. While this argument still is on, the Warsaw code have been integrated into the MESA software instrument as the module of radiostellar pulsations 2 years ago. And this opens this model for a wider user audience. The main reason behind these one-dimensional calculations is the calculation time cost of the multidimensional approach and the memory limitations of the old hardware. Just think about that back in the old days, the best computers consisted of multiple rooms. For example, this Atlas supercomputer in the University of Manchester. And they were operated through punch cards and punch tapes. Even the Commodore 64, the popular personal computer in the 80s and 90s, had 64 kilobytes of memory. And compare this to today's smartphones, which have several gigabytes of memories alongside the many higher computational capabilities. So these main limitations gone, and I didn't mention the modern supercomputers and GPU grids. So the hardware limitations are mostly gone. But for one dimension, the main picture is that we try to understand the three-dimensional convection, which could be like this in the box model, or this in an envelope model, or large eddy model, through the picture of the emerging eddies, the classic mixing length theory picture. And with this, we introduce the turbulent energy, a term which is described how much energy is stored in the turbulence and in the convecting motions. And this will introduce several free parameters by the number 7 or even 8. And these parameters were not calibrated in the past, and the lack of multi-dimensional codes also prevented the proper validation of the original assumptions. So the goal of my research is to check the validities and calibrate these models, and later use the multi-dimensional models to extend to non-radar modes and study the connection between convection and pulsation. The first part of this work is to calibrate the one-dimensional models to the observations and to the multi-dimensional codes. And meanwhile, I optimize the latter for a wider usage. Currently, from the last 10 years, the most prominent 3D codes are the Antares, the Cobalt, and the spheres. The Cobalt and the Antares is similar to each other. The former was used for modeling spectroscopic lines for cepheids, while the latter was developed for mostly solar-like convections. And they are the box models. So we have a box in the lower atmosphere of the star with the Eulerian grid. The Antares was used for cepheid stars, and the calibration for one-dimensional codes for the convective flux parameter. I will talk about that a bit later. The spheres is an envelope model and a large eddy simulation, and this was purposefully developed for pulsating stars, and it uses a hybrid Eulerian Lagrangian grid. Even the name comes from spherically Euler and radially Lagrangian scheme. And our research group has connections to both research group who develop these codes, and I currently use the spheres. So let's see the math behind our models. We started from the Navier-Stokes equations, the conservation of mass, the conservation of momentum, and the conservation of energy. And here I use the usual notations for the hydrodynamic quantities. And because our grid is limited, and turbulent motion, while it is macroscopic motion, but its scale goes very, very small scales. This is called the turbulent cascade. We cannot model through all the turbulent cascade, so we need a subgrid turbulence model, which comes with the introduction of a turbulent stress tensor, and with some new terms in the energy equation. This has 4 free parameters, but from the 4, these blue parameters are calibrated and experimented. Only the C parameter is somewhat not well tested. So we have only one really free parameter. So the first question is that is the 3D important because the computation times are enormous. The 3D computations to reach a full amplitude takes months, even half a year. I currently run these codes on the Hungarian Institute ELTE cloud on virtual computers, and there is calculations takes months, even for the 2D models. So the first question is there really need the 3D? And if we run a comparison, we can see that after convection sets in, we have almost the same structure for the star. On the we have the same number of convective cells, and we get the same quantities. This model has the notations as the previous one. Here we can see that how the energy, the velocities change and creates the convective cell, and in this model we can see these two. So we can stay at the two-dimensional. The other question is, we have slice a circle with defined opening degree, and we need enough degree, opening for describe the convection. So we should have convective cells, but we want to do the calculations in less time. So for this, I also ran a comparison for a 6-degree wide model, and 18-degree wide model, and the 30-degree wide model. And here from this video, we can see that after the convection sets in, in the 3 times wider model, we have the 3 times convective cells, and all in all, we only need the 6-degree wide model, which can fasten up more our calculations. These are needed if we want to make more models calculations in less time. But with these non-computation times causes we won't do any surveys. And we need use the old codes for this. But these new models has the better treatment of the non-radial effects. So we can use them as case studies and as a validation check for the older codes. And the modern programming language, for example, C++ in the case of the spheres, make them easier to read and easier to extend. And this is very good if we compare them to the older codes. They have the benefits as we know their behavior. They can describe the observations to a certain level, so they can use this as a reference for the multidimensional codes. And they have an economical computational time, so we can do surveys. But they are hard to grade because mostly they are written in mostly Fortran. And Fortran makes every attempt makes from every attempt of extension into hell. And besides, it is harder to parallelize and even faster more up these models. But their results can be used for multidimensional calculations. For example, currently, the starting velocities are always calculated from the one-dimensional linear non-adiabatic eigenfrequencies and eigenvectors, since they don't change too much in the nonlinear calculations, so the developing to full amplitude is faster. Maybe after proper calibration, one-dimensional full amplitude model can be converted and perturbed to the 2 or 3-dimensional one, and the relaxation time for forming the pulsation and the convections in this scenario will be less than a full run from the static start to the full amplitude. And if we can fasten these models up, we truly can concentrate on the multi-dimensional phenomena like the convection or even rotation and non-radial pulsations. In these new codes, we have good opportunities for parallelization. Today, scientists mostly use the open message person interface, which use multiple processes for parallelizations. This method has its drawback because if we have, because every process has its own virtual memory, so calculating with multiple processes on the same grid gives an epi overhead, and this will slow down the code later on. This can be avoided if we forget the OpenMPI. We should forget the OpenMPI for some time and use either native CPU threading. This is in the standard C++, for example, or we go to the full GPU parallelizations. To prove the benefit of this GPU threading, let's see a familiar system as if we make a star very simple, we get a harmonic oscillator system. And with this harmonic oscillator system, in this right-hand side, we can see the calculation time for against the number of elements in the linear chain in GPUs and in CPUs with different time steps. The calculations run for 200 model seconds, and we can see that the GPU threading, because we have many more cores and than the CPUs, way more faster, magnitudes faster. So we should try this. I don't say that the GPUs are the holy grail for the hydrocodes, but if we can reduce these computational times from months to days or just weeks, we have better opportunities. I work on this too, but it takes years to develop. And because of this, now we must step one back to step forward to in the future. So one-dimensional codes, we start from the previous multi-dimensional equations and transform them to one dimension. The convective gradient part of the velocity will become the eddy viscosity and turbulent pressure, and turbulent and convective part of the energy equations will become the convective flux. The turbulent energy, which is connected to the changing velocities and to the eddy viscosity and the turbulent pressure, has its own conservation equation and has its turbulent flux. The coupling is given between the two energy terms by the coupling term. And if we unfold these, we can see that we have many free parameters. The most eye-catching thing is that the classical alpha parameter for the mixing length theory is never alone, so it is just a measure term. But these other parameters should be calibrated in some way. But this was not done in the past, and there is no evidence in the literature for proper calibrations. There are recommended values. For example, in the 2019 paper of Paxson et al., they give 4 arbitrary parameter set based on the original Smolek paper. I want to calibrate these models, and to effectively handle the overview between the Budapest and Warsaw group, I include both models in my calibration. While RSP should have a better physical approach, it is nevertheless the case that the Budapest Florida can describe double bond pulsations. So maybe the physical picture is not the best in the Budapest Florida, but that means that we need some damping in that code. So there is not too much difference between the two codes. The Budapest Florida has no downward convection flux, and the RSP has convective flux, but they are written in Fortran, and this is the only difference between them. And my calibration process has 5 steps. I use currently the RRAB stars from Juchik et al. And because this way I have multiple stars with the same observation method. I excluded Balazs stars because Balazs effects cannot be modeled at the time, at this time currently, and chose those stars which have low error radial velocity measurements. I use radial velocities because these models don't have atmosphere above them, and this and while they are using bolometric luminosities, and this makes luminosity statistical stats rather difficult. Also, the luminosity amplitudes are well known that they are always higher than in the reality. So the first step is to find the proper helium adjudance, because the iron hydrogen index doesn't give us any clue about this. And after I keep from the best from them the best value for the sum of the errors, the square of some of the errors, and runs a larger parameter grid and calculate the pi square from them. And we will have multiple minima, but I chose this time the deepest minimum from them. And interesting questions: which parameters can we calibrate? As we can see here, with multiple parameter sets, I choose only one I change only one parameter, and this is described by the color of the given parameter: alpha p, alpha s, alpha d, alpha t, alpha nu, and alpha c. And we can see that only 3 of them has effect on the velocity curve. The other 3 has almost nothing effect in this case, but they have their effect in the model selection. So we need them, but we can't get them from the observed velocities. And that is another numerical challenge, because there is an amplitude change which is affected by the size of the time step, and this will cause in islands in my results. You will see this in this next picture here. These are the islands which are caused by the numerical uncertainties, and in this model we have 400 models, and this cross is the previously recommended alpha nu and alpha d parameter. The color describes the chi square, the chi square. And alpha S was almost the same for every model, so I didn't make a picture from it. And if we can see that we have a valley and a narrower, deeper valley inside it. And if we zoom into it, we can see this bird eating something. This bird is the border of the 5% p-value. So for the acceptance in my calculations. And we can see that alpha D has a higher error, and in the other models we can see this 2. And currently there is 4 stars here. And if we sum this up, we get these results for alpha nu and alpha D. This black dot represents the RSP set A, while the old BPF set is this cross. Maybe there is a temperature dependence here, because V9 and has somewhat larger temperature than these 2, which has the similar temperature, and V46 has a lower temperature. And this can physically described by the fact that if we lower temperature, we have stronger convection. But if one may try to convert these into the RSP, must face the fact that this is not only a simple parameter conversion because of the handling of the convection. In this plot, this video, we can see the energy and turbulent energy profiles, the luminosity profiles for the radiative, convective, and turbulent luminosities, the ionizations, the luminosity phase, the capacities and temperatures, and the limit cycle and the phase space. And we can see that in the RSP model, with the same parameters, convective parameters, we get higher amplitudes everywhere. And the other thing which was argued by Smolak and Moskalik, that in the proper physical way, we should need this kind of turbulent energies, while Budapest fluoride has an overshooting, and this means, and this is a damping. So I will need to repeat the whole calibrating process for the RSP2. But we can calibrate to the 2D codes, and this was firstly done for the alpha C parameter by Mudpret at all 6 years ago. And they found that the alpha C parameter has always time dependence, phase dependence. Here we can see ET values calculated from only the vertical and the horizontal velocities with different radiative damping. And I want to reinforce these results by the spheres and extend it to the other alpha parameters. And it is an interesting question that what changes in the RLIs, since we know that these the 2 type of star has 2 sets of parameters. So for this, we have the one-dimensional convective terms. We have the transforming from the 2D to 1D, and I use the original before the simplifications terms, and from them calculate the eddy viscosity and the other parameters. Alpha P parameter has no other comparable term, so it remains 2/3. So for my preliminary results, we can see here a plot, left-hand side, the earlier slice plot with the convection, right-hand side, luminosity, the phase of the luminosity of the model. And in this bottom left, we can see the 4 parameters, how they changes in time. The alpha t, alpha c, and alpha nu parameters are to the left y-axis, while the alpha d has the right y-axis because it has a higher value. So we can see that indeed these are changing in a way. Alpha nu has some correlation with the phase and with the maxima, while alpha t has something like the anti-correlation. So this is an ongoing research, and this will be continued by the calibration of the RSP, and I will extend it to for the other variable types such as the RRCs and cepheid. And with these results, I will study the differences with the 2-dimensional and 1-dimensional code, and we work on a method to speed up the 2-dimensional models. While the second part of my study is the search for non-radial modes in the multi-D models, and later to convert the spheres to GPUs to speed up calculations even more. So the main takeaway is that the topic of classical stellar pulsations is not even nearly closed. There's a bunch of old and new mysteries and questions that are waiting for solutions. Our current 1-dimensional calculations reach their limits, but the 2- and 3-dimensional solutions are not fast enough yet to get surveys, but we can use them as case studies, as well as a validation check for the 1-dimensional models, while the 1-dimensional model can be used to speed up the 2- and 3-dimensional codes. And thank you for your attention.
Thank you very much, Gábor, for your talk. So I think we have time for questions. So I invite everyone in the audience to go ahead. So, okay, I see that. So there's no questions yet. So I was, okay, 2 hands were just raised right now. So I didn't see which one was the first one. So I would just arbitrarily give the floor to Adrian. Go ahead, Adrian. You can ask your question. Okay, so maybe Herbert first.
I didn't hear anything.
No, I didn't hear anything either. It's just that it maybe
Yes,
doesn't.
sorry.
Good. Okay.
I had some problem with audio. Thank you so much, Gábor, for your nice talk. I would like to address you a question about the possibility of detecting real-time stellar evolution, taking into account, I guess, you are dealing with different time scales when you study simultaneously pulsation and convection.
Yes, in these models, the evolution is not taken into account, and mostly because firstly the time scales, as you said, and the other thing that we cannot, these models are not fast enough to take into the time for the evolution of a star into account. And a few years ago, Kuka said on the in a conference that in the age of of our processors. Before the age of the quantum processors, we won't have these kind of evolution and pulsation models with multiple dimensions.
Mm-hmm. Okay, thank you. Just one more. Is it possible to have the, because when you consider convection, in somehow you are considering energy redistribution, especially when you have 2D models or 3D models. Can it explain the pulsation suppression in some stellar in some stars? I mean, when you consider 2D models or 3D models and convection, are you able to explain why some stars, they have no modes, they do not pulsate at all?
It can be showed. For example, if we can calculate the working integrants for the two and 3 dimensional models in the same way as for the 1-dimensional models. For example, the Moodpracht et al. They did the same for to show the difference between the multi-dimension, the Pufus model, and the Sterling-Berg model. And this way you can calculate the excitement of multiple modes.
Okay, thank you so much.
Thank you.
Thank you. Then we had another hand raised, Herbert Mutsam. The floor is yours if you want to ask your question. Another issue with the audio. Herbert, are you ready to ask your question?
Is it? Can you hear me now?
Yes, now it's okay.
Very well. Herbert Mutzam from Vienna. Many thanks first for your interesting work you're reporting. I have 1 or 2 questions, I don't know. So first you may have mentioned, but I have perhaps not got it. The code you are using now for mainly 2D calculation, is it an outgrowth of the Spheres code? Or is it the Spheres code?
The Spheres code can do 3D and 2D calculations too.
I see. The second question is atmosphere. How many points do you have in the atmosphere, and is it very difficult for parallel stars to work with the atmosphere? Because with Cepheids, we had most problems in the atmosphere and slightly below.
So above the photosphere, we have about 10, 20, between 10 and 20 cell mass cells, and but there is no atmosphere model above them.
10, 20 points of what sort? I didn't quite get it.
For example, here. So the photosphere in this picture is somewhere here, and above that there is 10 layers.
Okay. Yeah. Thank you.
Thank you for your question.
Okay, thank you very much for your questions. Do we have another question? We have time for 1 other question if you want. Yes, I see Messao raise his hand. Go ahead.
Okay. Okay. Thank you very much for the interesting talk. My question is about turbulence modeling. I think you mentioned that you assume one particular type of subgrid model of turbulence. Is that correct?
Yes.
Yeah. And is there any reason why you stick to that one particular model? I hear that this kind of simulation depends on that kind of model, crucially.
This model was this subtype subgrid model was chosen by the original developer Dupré, and currently I use their model and want to develop extend it, and we stick with their model selections.
So you do not have any plan to try other models in the future?
Yeah. So we can and we should try other subgrid models later on.
Okay. Thank you.
So a plan for future works. So I will thank everyone now for taking part. Thank you very much, Gábor, for a very interesting talk. And I'll see you next year. So have a happy holidays to everyone. Maybe the steering committee can stay put. And see you, everyone. Bye-bye. Thank you.
Thank you for the
Goodbye.
Bye.